All right, let's jump right into this explainer. We're putting on our detective hats today to figure out exactly how we know what we know about our changing climate. We hear about it constantly, right? But today, we're going to tune out the noise and look strictly at the data to see what kind of story it actually tells us. Now, to solve any mystery, you got to start with the big question, the one that frames the whole investigation. Why should we be concerned about climate change? And to truly answer this, well, we can't just guess. We need to examine the evidence left behind over centuries and even millennia, literally treating it like a detective at a crime scene. So here's our agenda for the investigation. First, trusting climate change evidence. Second, decoding ancient ice cores. Third, proxy data like art and diaries. Fourth, modern temperature and sea ice. And finally, number 5, ranking the evidence to deliver our final verdict. All right, Section 1, trusting climate change evidence. Before we dig into the physical clues, we really need to understand the lens through which we're going to evaluate all of this evidence. The absolute crucial point here is reliability. We're talking about the accuracy of the data and the extent to which it actually represents the real world. This is the whole shebang. It's what allows us to have real confidence in the evidence. As we review our witnesses today, we have to constantly ask ourselves, does this data accurately reflect reality? Can we truly trust it? Moving on to Section 2, decoding ancient ice cores. Our very first witness is basically the ultimate ancient archive, literally taking us back up to 800,000 years into the past. What's really fascinating here is seeing a physical piece of ancient climate history. It's a literal time capsule right there in a researcher's hands. Sampled from these incredibly remote, freezing places like Antarctica and Greenland, these ice cores give us this deep, deep historical evidence of climate shifts that happened way, way before humans ever started keeping records. It's kind of mind-blowing how this natural archive actually builds up. Over roughly 30 years, snow falls and just naturally compresses under its own weight. First, it turns into granular ice, then it gets denser into a state called firn, and finally, it transitions into rock-solid glacial ice. Now here's the crazy part. As it compresses, it traps about 20% air as these tiny microscopic bubbles inside the ice. Those bubbles contain the actual, literal, ancient atmospheric composition that scientists can just pop open and analyze in a lab today. But let's weigh the reliability of these ice cores, because it's an interesting balance. On the more reliable side, we get data covering a massive time frame, up to 800,000 years, and we use highly accurate lab equipment to analyze it. But we've got to be fair and acknowledge the less reliable aspects too. We can't always pinpoint the exact year, and they don't just spit out a neat temperature reading. Instead, scientists have to make inferences based on oxygen isotopes. Plus, they're only sampled from a few polar locations, right? So we have to ask if they perfectly represent the entire planet's temperature. Okay, Section 3, proxy data, specifically art and diaries. So now we're shifting gears from the hard, frozen science of ice cores to the much more subjective world of human experience. Look at these two vastly different historical records. On one hand, you have a classic painting of a frost fair taking place right on the completely frozen River Thames in London. Crazy to think about, right? And on the other hand, we have the beautifully vibrant cherry blossoms of Kyoto, Japan. People have meticulously recorded the exact dates these blossoms peaked for generations. Both of these clues, totally different as they are, give us absolutely vital insights into past climates. These centuries of annual diary entries give us what's known as human proxy data, or inferred data. And honestly, this blows my mind. Japanese cherry blossom peak bloom dates have been recorded since the year 812 AD. That is wild. Similarly, records of European grape harvests date all the way back to 1354. Because everyday folks recorded these annually for so many centuries, it actually allows us to do quantitative analysis on historical weather trends. So let's put this human proxy data to the reliability test. On the more reliable side, we can verify events by cross-referencing different diaries. If multiple independent diaries from the exact same town say a river froze solid, it's highly likely it actually did. But we really have to be careful with the less reliable elements, especially with art. There are actually very few landscape paintings produced before 1750, and the ones we do have were often super romanticized. A painter might deliberately exaggerate how harsh a winter was just for dramatic artistic effect, making it highly subjective. Plus, it's all indirect proxy data. We can't just look at a painting and know exactly what the temperature was that day. Moving right along to Section 4, modern temperature and sea ice.
Leaving the historical diaries and paintings behind, we are now entering the era of strict, quantitative, modern instruments.
And the story these modern thermometers are telling us is pretty undeniable. When you track the annual mean land temperature starting way back around 1880, you naturally see variations, ups and downs. But as we move toward the present day, there is this sharp, stark upward trend of consecutive warming years. The data from our modern instruments is just incredibly clear about this recent warming pattern. If we zoom in and look closer at regional impacts rather than just the global averages, the UK actually recorded a really significant milestone recently. When comparing the historical baseline to 2022, the UK's annual average temperature crossed 10 degrees Celsius for the very first time. That's a precise quantitative measurement showing a definitive shift in the real-world climate baseline. Now, our final piece of evidence in this investigation takes us to the freezing waters of the far north. The Arctic Ocean gives us another absolutely crucial, measurable metric to look at: the physical changes in the sea ice. And I gotta tell you, the numbers we're tracking here are drastic: 13.4%. Since 1979, the Arctic sea ice extent minimum has heavily declined by 13.4% every single decade. But wait, the melting is actually accelerating. Just looking at the window from 2003 to 2015, the sea ice extent reduced even faster, plummeting from 6.5 million square kilometers down to just 3.5 million. Think about that for a second. That is a massive loss of 3 million square kilometers of sea ice in just over a decade. It's a huge indicator of a rapidly warming Arctic environment. All right, that brings us to Section 5, ranking the evidence. We've interrogated all 4 of our witnesses today, and now the final judgment is really up to you. Looking back at our complete evidence roster, we've got the incredibly long-term scope of ice cores trapping those ancient atmospheres. We've got the modern, stark tracking of sea ice positions. We've looked at the beautiful, kind of subjective humanity of historical diaries and paintings. And finally, the strict, hard numbers of global temperature data from thermometers. Knowing that no single piece of evidence is perfectly flawless, because let's face it, science is messy, how would you actually rank these from 1 to 4? Like, how do you personally weigh exact modern numbers against centuries of historical records? Take a moment and really think about how you justify your choices. But as we wrap up this investigation, I want to leave you with this one final thought. What does it tell us that, despite all their individual limitations, all 4 of these vastly different witnesses point to the exact same undeniable conclusion about our warming world? Thanks for joining me on this explainer, and hey, keep asking the big questions.